Hello, welcome everybody. We will just start in 60 seconds, waiting for some more people to join. All right. Good afternoon, everyone, and welcome to today's session. Thank you for taking the time to join us. We really appreciate it. My name is Amol, and I will be your host today for BM Process Management. At BM Process, we work closely with companies in tank storage, chemical, and industrial sectors, helping them with emission controls and process related challenges. And the one thing we see again and again is this: many safety related decisions are not ignored, they are misunderstood, especially when it comes to explosion safety. Let me start with a simple question, and you can chat if you want. How many of you have faced this situation? You're working on a system, and suddenly the question comes up: do we have a flame arrestor here? You check standards, you look at the previous projects, you ask your colleagues around, and still the answer is not fully clear. And this is exactly why we are here today. Because topics like flame arrestors, gas groups, deflagration versus detonation, they do sound technical, but in reality, they are about one thing: making the right decision before something goes wrong, especially when it comes to safety. You can see on your screen, there are three speakers, and we are going to have more conversation with them in the coming minutes. You're going to learn these five things: different behavior of exposure in the real systems, what are the gas groups and MESG, sorry for tongue twister. We are going to simplify it, and the correct flame arrestor selection, common mistakes in projects that usually we can do, and the practical design and safety decisions. We want you to walk away with the practical guidance and together how to make safer, smarter, and more cost effective decisions in your day-to-day work. Some practical advice: by default, all of you are on mute. And if you have any questions, put it either question and answer, or you can also chat with us on the chat function. And we're also going to have some quiz around so that conversation is two-way and more interactive. So here are our three amazing speakers for today. Bart, he's a managing director and senior process engineer, and also acts as a consultant and specializing in industrial emission control and process safety. Bart supports company in selecting and optimizing VOC treatment and safety system with a practical, independent approach. Then we have Anya. She's the head of sales and marketing at KITO. You will learn more about KITO also in the upcoming slides. Anya supports customers with technical expertise and a solution-oriented mindset. She helps them select the right devices for their application and build long-term reliable partnership. Then we have Mark. He's a product specialist at Ritec BV. As a product specialist at Ritec, Mark advises customer optimize technical solutions and translate complex product knowledge into practical application that help companies work more efficiently and reliably. You will find them on LinkedIn. You can also check the website to learn more about them, and feel free to get in touch with them for in terms of any questions or advice that you're looking for. So let's check whether your system is working in terms of quiz, and you can see them on your main screen. So just give me 1 second, they are loading. Yes. So the first quiz for us, you are designing a tank system. What is the safest decision that you will make? Will you install a frame arrestor everywhere just to be safe? Will you follow what was done in the last project? Will you check standards quickly and decide? Or you will understand the gas process and risk first? Let's see. I got 11 responses, 15. As you can see, most of us, we think it's important to understand the gas process and risky first. And that is the correct answer. Because we have seen A, B, and C, the 1, 2, 3 answers happening often in real projects. And that's what exactly we are going to discuss in today's session. So if you are ready, we can invite our first speaker, Bart, and I can close this presentation and start with his slides. Bart, in the meantime, if you're ready, I would like to have you on the screen.
Yes, Samuel, thank you. I'm ready.
Yes, welcome. All to you.
Okay, thank you. Hi there, I'm Bart. Good afternoon, everyone, and thank you for joining. I'm happy to see the answers in the first quiz. That's actually good news, I think. For those of you who don't know us yet, we are an expert group. We handle general process, but we have a strong emphasis on, let's say, off-gas treatment and the handling of explosive gases, and we are active throughout the entire of the EU. A large field of work for us is, for example, oil and gas and general process industries. If you want to see more about us and the guys that we work with, feel free to reach out afterwards or to look it up on our website. So why are we here today? I like to share what I know, and I like to help you to learn a few things if I can. Now, why do I choose to do this? It is because in our day-to-day projects, we very often see that, let's say, the whole explosion protection, flame arrestors, and how to choose them is not always very clear. For us, it is key that you understand the whole process, and that is what today is all about. Next slide, please. So I'm pretty sure that you all know this guy. When I was a small kid, I really loved this, and to be honest, I still do. He always makes very smart plans, but in real life, it doesn't turn out as he expected. And that's the same in actual process design, because in real life, it can often lead to real life events that don't go as you planned or designed for. So that's why I would like to start with an example from our day-to-day work that shows how we hopefully prevented such a thing from happening. So let's go back to 2025, a client in Rotterdam. You see here 4 key steps that I wrote down. This client wanted to store a new product. Previously, the products he stored were in gas group 2A, and the new product fell into gas group 2B3. That required a complete review of the whole explosion protection and therefore, of course, also of the flame arrestors. By the way, previously they used inline flame arrestors underneath of the breather valves, which in itself is not exactly optimal because there you can't really see what's happening. You don't know if they're blocked. Problematic. But also, we changed the whole tank protection because we also moved into a plant where we would actively extract the off gas. So that actually required that we also review all of the breather valves, the pressures, and this and that. So based on that, we plan to install a breather valve for the day-to-day breathing. So not for the low pressure protection, but just for the day-to-day breathing, because the outlet of the off-gas was handled by the off-gas treatment. And of course, we also need to breathe in air when you need to. Now, the question that we had is, do we need a flame arrestor on this valve? Normally, I think the answer would be, yeah, of course, because more protection seems like a good idea. But I said, well, I'm not so sure. Let's do the proper route and let's do a proper HAZOP only of this part. So with our beautiful tool, which you can learn about if you look back our previous event, we did the HAZOP of this actual case. And there we also looked at the cold hard data. And there it was proven that the risk of sparks or flames being sucked into the tank are actually super low. However, the risk of blocking due to the fact that it freezes up, for example, when it's cold and wet, which happens a lot over here, is way higher. So in the end, we also got background data that this actually happened quite a few times over the past years nearby, where actual tanks failed due to this case. So in the end, we said, okay, based on the cold hard facts and the fact that we look at not only the explosion protection part, but at the whole thing, we will not install a flame arrestor on this breather valve. So I think this is a pretty good example of that more equipment doesn't always mean that it is actually safer. You need to understand the risks to have a proper process design. Next slide, please. So why does this go wrong? I split it up into three main groups. First of all, we see that we tend to properly assume and not go actually in depth. The other point is that we look at equipment, but not at the whole process. And the last one, I think that is even more happening in real life, is that we all, at least me, myself, are pretty much risk averse. So we want to ensure that we avoid risk, and where it might be smarter to see, okay, but what would be the right idea to do here? Because we always want to go for more is also more safe. But there you could ignore, for example, pressure drop, the fact that it can freeze over. And what we also, at least me, see very often in practice is that flame arrestors have been made, have been placed, but you can't reach the bloody thing if you want to have work done on it. So there's also a part on where do I actually place it so I can do what is actually needed. So if you have a clear view of the whole process, that will lead to the fact that you do better in the entire process design. Next slide, please. So that brings me actually to what is the goal of now, today. The goal of this is that we talked about the three parts that I just said, and I actually did add one more. Use the actual expertise when you really need it. We have a lot of it, I think, me and my team, but also if we don't know, we call the experts. That's why I'm very happy with the guests that we have with us today, because in past projects, they've really helped us out. And in the end, that is the goal. We want to help the client. And that's why I would like to go into a deep dive on how to do all of this in practice and how this equipment actually works. So I will talk to you again in the Q&A at the end, and Amol, back to you.
Thank you, Bart. Good intro and sharing some practical and real life examples. And as you said, let's move from principle to practice. So in a couple of seconds, I would like to get our, oops, sometimes it's a different story. Okay, let me see, present. All right, so I would like to invite on the screen our two guests and the experts with whom BM Process Management has worked successfully. So, Anya and Mark, welcome.
Thank you. Welcome, and thank you for your introduction, Amel and Bart. We are happy to be here.
Over to you.
Okay.
Hello, I am Mark van der Zeepen from the company Ritec. We are near Ghent in Belgium, and our CEO Rick van der Bussen started the company in 1996. So we are existing 30 years. And some other numbers, I'm almost 25 years at Ritec. We started with rupture discs of BSMB, which you can see here. Still our biggest supplier. But 10 years ago, we started to distribute KITO GmbH in Belgium and Luxembourg. So I'm very pleased with the collaboration. And then finally, when our colleagues in the Netherlands in Emmeloord stopped their business, the company Truevals, now 1 year, we are also distributing KITO in the Netherlands. Over to you, Anya.
Thank you. Yeah, my name is Anya. I'm at KITO now for about 15 years, but worked before at another company also producing flame arresters. So I'm in this field quite a long time. KITO is a mid-sized company based in Braunschweig, so in the north of Germany. If you ever go on the famous highway A2, you are highly invited to have a short stop. We have the production here. We are more or less 85 people. Everything is produced here in Germany, and the KITO brand is known since 1928, so it's one of the oldest brands. And just to give you a short back information, KITO comes from the German word Kiestopf, so which means is a pot filled with gravel, so with small stones. And that was the design of the first flame arrestor. Between these gravel stones, you have a gap, and this was used to quench the flame, but of course that is no longer state of the art. So nowadays, Bart already mentioned that why to install a flame arrestor or a breather valve, and we would like to show you some examples on the next slide where it is more or less explaining where to use. So if you start exactly the left movie, thanks for that, we see that already a severe incident is happening. So one tank is already affected. And of course, although the fire brigade is doing the best, the tanks next by are also affected, and everybody can see what is happening if something is happening to one tank, and it is not a standalone installation. So it will be very clear that that is severe. On the right movie, we have a completely different source of ignition. You see there's a man coming just wrapping with a tissue, and he's creating a spark due to electrostatic electricity. And that can already be enough to ignite the atmosphere around the tank. So just two short examples, what can happen even if it's not very clear that there is a risk. So we would like to give you some more information about the famous world of explosion protection by flame arresters.
Anya, when we have to deal with an explosive atmosphere and we as an owner cannot avoid that atmosphere, what shall we do?
Yeah, thank you. That's a very good question. And of course, the first aim is to avoid the explosive atmosphere, as Mark said. We always need three things. We need a flammable product, we need an ignition source, and we need oxygen. If we can be sure that one of these elements is missing, we are on the safe side. But often that's not the case in reality, sometimes even only in startup or shutdown processes. So when we need a flame arrestor, that's a big field. So what do we need to know? There are different designs of flame arresters, end of line, inline, so we need to know the application. And we want to have a deeper look in this famous MESG, maximum experimental safe gap, because that gives us an idea how dangerous the product is. And as shown on the video below, thank you for starting that, Amol, we see how the flame arrestor in pipes is working. So we see the flow coming from the side. Maybe we can see it again. Thank you. And in the flame arrestor element itself, the flame is quenched. So a flame arrestor is stopping the propagation from an explosion from one part of the installation to another part of the installation. Thank you. Let's go to the next slide. Okay. We already spoke about this famous maximum experimental safe gap, and I want to share quickly how it is measured, because it is really important to understand what this value is giving to you. It's like the passport of the flammable product. We see here on the left side a photo, on the right side a cut drawing of this apparatus. So we have an inner volume, which is filled with the product I want to measure with air in the most dangerous stoichiometric mixture. And via a small gap, it is connected to an outer volume. So then it will be ignited on purpose. And of course, the explosion tries to go into the direction of the unburned gases, means from the internal volume to the external volume. You see there's a sight glass, and in case the explosion reaches the outer volume, you will see it on the sight glass. Now, with a micrometric screw, you can narrow this gap, and there will be one value where this secondary explosion can no longer happen. And this value is the maximum experimental safe gap given in millimeters. So now you might ask, well, I have here several products, but where do I find this? We have given here a link from a public open database where you can check explosive parameters. You can search by name, by CAS number, by some formula, and you will find for really a lot of products information, because on the general safety data sheets, we will find often a lot of information, but not in regard of the explosive limits. So important is to know MESG, maximum experimental safe gap, is a very important parameter for a flammable product. Next slide, please.
Well, here you see the groups, and the governing organizations have divided the various gases in groups from 2A1, the least dangerous gases, burning slowly like methane or biogas, up to 2C, which are violently burning gases like hydrogen. And that's because it makes no sense to design a flame arrestor for each gas. It will be unworkable. So by dividing into groups, then the manufacturers can create a flame arrestor, for instance, suitable for 2B3, and this flame arrestor will stop all the gases from 2B3 and the underlying groups from 2A1 up to 2B3. There are not so much gases in the groups 2B and 2C, so if you are designing a multi-purpose tank for a tank farm, it could be saving money and pressure drop if you select, for instance, 2B3, because it will cover more than 90% of the gases.
Yeah. And maybe just as amendment, here we talk about these subgroups of the group 2B, and those who are familiar with the electrical world, there it is not that common. And in the electrical world, you see explosion group 2B and then a temperature class T. What we see sometimes in the data sheet we receive, but the electrical way of explosion groups is completely different than for flame arresters. So please, if you see something with T, that is not referring to the product in means of explosion groups. Thank you. Next slide, please. Yeah, I just want to invite you to have your own flame arrestor. If you can scan the QR code, you will get a grid. And we can also share later the link in case you cannot do that as you use your mobile phone. On the photo, you see the typical design of a flame arrestor element. We have this grid. It's a so-called crimped ribbon type. So a flat and a crimped ribbon, they are wound together. And depending on the tooth wheel on the machine, we can create the specific width of gap, which is most important. And here I want to point out that it is really important to not mix up the MESG, which we have heard before, and the width of gap, which is in the device. The MESG is measured under laboratory conditions. So we have a determined length of the gap, which can be completely different at the flame arrestor element of a device. Additionally, a flame arrestor can be used for different explosion processes, and therefore a different design of the flame arrestor element is necessary. So do not mix it saying, oh, I have a 2B3 product, so automatically my width of gap needs to have the same value. That is not the case. For you is important what is on the tag plate, what is on the certificate, on the declaration of conformity, for which explosion process and for which explosion group the flame arrestor is approved. Next slide, please. And here we come to the first quiz. Amol, thank you for sharing your quiz. Okay, so please have a look. MESG versus width of gap in flame arrestor. What is correct? We have possibility. MESG is a characteristic of the flammable product. The width of gap is a design detail of the arrestor. Or the gap in the flame arrestor must be equal to the MESG. The width of a gap in a flame arrestor. MESG and width of gap are identical values used interchangeably in practice. So I'm wondering what is the result? And very well listened. So what is happening here? The gap in the flame arrestor must not be equal, has not to be equal. That's what I was trying to explain. It's often the case that the width of gap is smaller than the MESG, but it's not the case, for example, if you have an end-of-line flame arrestor, which stops an atmospheric deflagration with low pressures. So please have a look for what the arrestor is approved, the manufacturer is offering to you. It is not the same. Thank you. Okay, so Mark, what are risks?
Here we see a thunderstorm approaching, and we will put a breather valve on top of the tank, but a valve without integrated flame arrestors. If you're lucky, the lightning will not pass, but if the valve is inbreathing or outbreathing, oh no, that was a flare system.
Yeah, I think we need to go back one slide, huh? Yeah, thank you. No, one slide before. Okay. Yeah, and now start.
Yeah, that's the flare, but no matter. You see the yellow pipe to the flare?
It's correct. Continue.
Here is the lightning strike.
Yeah.
Here is the valve, no flame arrestor. You're not lucky because it passes through.
Yeah, that is a bit what Bart had in the beginning. Huh? So if your tank is not protected and then sunny day and then in the evening it's getting cold, lightning from the thunderstorm, we will all not be happy. Okay, so now comes, no, that is again, that is the same. Yeah.
The lightning.
Yeah, so then next.
Here we have the flashback from the flare. The yellow pipe is driving the gases through the flare, but the flare is burning continuously, so that's more dangerous than a lightning strike. And if you do not have a flame arrestor there, you can have a flashback. from the flare and an ignition in the tank, which you see here.
Okay, so that was a very good example for an explosion process in a pipeline, which will bring us to the next slide, please. Okay.
Well, Anja, what is going to happen when an explosion is traveling through a pipeline?
Yeah, that is very important to understand. So here we have on the right-hand side the flame arrestor, on the left-hand side what we see as the source of ignition, as maybe the flare Mark explained in the previous slide. So what is happening? There is an ignition and the vapor-air mixture in the pipe is ignited. So the flame front will spread into the direction of the unburned gases. At the beginning, the velocity is quite low and the pressure is quite low. But as there is more food for the flame, it will be quicker and quicker. And there's one time or a zone, the so-called transition zone, where pressure and flame front meet. And here we have the unstable detonation, which is occurring only in milliseconds, and no one can predict exactly where that will happen. And after that point, a stable detonation is developing with much higher pressures and velocities. And therefore, it is easy to understand that a flame arrestor, which needs to stop a detonation, must be designed differently than a flame arrestor which will stop a deflagration. And Mark, how can we determine where we can use a deflagration arrestor and where we can use a detonation arrestor?
Well, there is a rule of thumb, and that's the famous L over D. So the D is the diameter of the pipe and the L is the length. And you can see it depends on the gas groups. So the slow burning gases up to 2B3, let's say alcohols or methane, it's 50 pipe diameters before you reach that transition zone. So if you put the flame arrestor close enough to the ignition source for those gases, within 50 times the pipe diameter, so DN100 pipe 4-inch, it's 5 meters, and then you are sure that this flame is still in its slow speed stage, the deflagration. Further, let's say at 100 meters, there you should will be in a detonation, and you need a detonation arrestor. But for 2C gases like hydrogen, this transition zone is closer to the source of ignition. So be aware it's 30 times the pipe diameter, so 3 meters in a DN100 pipe.
Yeah. Thank you for explaining that so well. And here again, every manufacturer needs to state exactly for which L over D ratio the deflagration arrestor is tested. These L over D values are the maximum allowed from the standard. It can be that a manufacturer has tested a deflagration arrestor for a smaller L over D, but then it's clearly stated in the description and on the tech plate. Okay, then we can go to the next slide, which gives us a short overview where you have applications for flame arrestors. So simply spoken, everywhere where flammable products under atmospheric conditions are stored, handled, loaded, unloaded, or burned, from vapor recovery units to tank storage farms to biogas applications, ethanol, liquor plants, everywhere a flame arrestor is a good choice. Okay, the next slide, please. Yeah.
So in summary, Anja, which are actually the parameters that you really need to consider for a design of a flame arrestor?
Yeah, that is the most important question. What do we need to know to give you the best possible support? Of course, we need to know about which product are we speaking. Bart said in the beginning there was a change in product in the tank. That makes a big difference in the flame arrestors you may need in case the explosion group is changing. So first we need to know which product. Then what is the explosion process which may occur? Does it come from the atmosphere or does it come from a pipeline, as we learned before deflagration detonation? Of course, the flame arrestor needs to be designed for the operational conditions, means must be resistant against corrosion, the temperature and special specifications need to be considered, and temperature and pressures needs also to be double checked. Flame arresters are in general approved for atmospheric conditions. They are defined up to 60 degrees Celsius and 1.2 bar absolute. But there are as well devices which are approved for higher pressures and temperatures, but that must be known. And of course, for the operator, it's very important, especially for inline arresters, that the pressure drop they are causing is not too high to let the system run best. All right, then we come to the next slide, and it's quiz time again. Okay, I think that is hopefully now an easy question. What's the difference between deflagration and detonation? A deflagration propagates slower than the speed of sound, a detonation faster. A deflagration occurs only underwater, a detonation only in air. A deflagration requires no fuel, a detonation does. So please, your votes. Okay. Yeah, of course, that what we have learned, both are explosion processes in pipes, and yeah, a detonation has higher pressures and higher velocities. All right, and we go to the next slide. Yeah, we want to point out one document which can be really interesting. It's the CEN guide. It's a guideline for flame arresters. So it is not really a law, but it gives really helpful information such as definitions and as well here installation limits. Mark, what we are facing often is this question about nominal pipe sizes connected to flame arresters.
Yes, and that's an important one because sometimes it appears only late in the stage after the flame arrestor has been ordered, because we do not have the full picture. But the issue is that flame arresters are certified by notified bodies in certain conditions, and one of the conditions is that the nominal size of the pipeline at the site where the ignition is, which is called the unprotected sites, shall be either equal or less. And sometimes we see that this is not the real situation, that there is a reduction. As you can see in the next slide, we were working on a project, and we had already defined the flame arresters, but our customer needed step files and then sent the nice picture of the complete installation. And all of a sudden we discovered the central zone is a reduction. The flame is coming from below and a DN150 pipe, but some measurement equipments in the middle, they have a DN100. And then we go back to DN150 to the detonation arrestor, which you see on top. The reduction there from DN100 to DN150 can cause unstable behavior, and the flame arrestor could therefore not be able to stop the flame because it has been tested, certified as if it were a DN150 pipe without restrictions.
Yeah, and the smaller size lead to increase in pressure and velocity. So the explosion process behavior is changed. So as you see on the right photo, that is a really big mistake. So please always be aware. Maybe you can ask for the IOM before or ask the manufacturer, or as we were here lucky to get the installation which was planned, so we could give an advice before it was too late. Next slide, please. Yeah.
Anja, I have a question. Which one of these two do you think is the best solution?
Yeah, that's a nice question. And as it said, the left side has a lot of advantages. On the right side, for explanation, we see two devices in connection installed, an inline flame arrestor and an end-of-line breather valve. And there are several disadvantages of the right-hand side. Of course, an inline flame arrestor is heavier and has a stronger flame arrestor element. The risk of clogging is higher as it is inline installed, and maintenance, what Bart also mentioned in the beginning, is more difficult. But the main point is that the behavior of an inline flame arrestor connected to an end-of-line valve will be different, because as Mark said, it is tested in a different way. And nowadays, the valid international standard requires that both devices are tested together as a unit. And that is often not the case what we see in the field. That's often an American way of thinking, installing inline arrestor and end-of-line breather valve. Whereas on the left-hand side, you have a combined unit. So you combine the both functions, safety against explosion and in and out breathing in one device. So costs might be lower, weight is lower, which is often important on a tank. And the flame arrestor element is connected to the atmosphere from where the ignition is expected. So first the flame is quenched and then it comes to the valve. And additionally, the inspection is much easier. You see on the vacuum side, the flame arrestor element is in direct contact to the atmosphere, so it's visible. And so we highly recommend only to use the left-hand side, which we will explain in the next slides a bit more, or to show the function a bit more in detail. Yeah.
Yeah, here we can see quickly the overpressure event of such a valve. The tank is on the bottom. On the top is the overpressure pallet. So the tank vapors, they push the pallet up and they can escape to the left. If there is an ignition from a lightning strike, it tries to get in from the left to the right, but the flame arrestor there will stop it.
Yeah, and on the next slide, we will see the vacuum side. Yeah, so here it's a bit the same. The air is sucked from the outside, air can breathe in, and in case of an ignition, flames are stopped at the flame arrestor element. So an easy unit giving you both function, safety, and in and out breathing. Which brings us to another risk on the next slide. So what do we have here?
Fire, an external pool fire. So there is a spell product outside of the tank gets into fire. And you need to protect the tank because a lot of energy will go into the tank, it creates a lot of vapor. And there you have the typical emergency vent, which will open and relieve a huge amount of vapors.
Yeah. And on the next slide, we can talk a bit about when do we use an emergency vent. Just a short difference between DIN tanks, as we are more familiar with in Germany, and API tanks. DIN tanks are designed with a weak seam. That means in case of fire, it is foreseen that the seam between the shell and the roof will break. And like an oyster, it will open, and there the big volume flows, as Mark said, will escape. But API tanks are differently designed. And for those, an emergency vent is the standard unit. And just a word for two very common standards, API 650 and API 620, because the difference will be how you set your emergency vent. Because only one, the API 620, allows that you go higher than the maximum allowable working pressure once the emergency vent is opening. Every valve is working with a certain accumulation, and API 620 allows to go 20% above. Whereas in API 650, you need to be sure that when the emergency vent is opening, it is fully open at the maximum allowable working pressure of the tank. That is an interesting point when it comes to settings of valves, which we will see on the next slide.
Here we have an example where you can see it's a tank with a design pressure of 10 millibar. And the emergency vent here has 20% overpressure, so it's set at 83. In case of overpressure, it will open, it will be fully open at 99, of 9.9 millibar, fully relieving the flow, so you won't get a pressure higher than 10 millibar in the tank. But here you see also a normal valve, which is breathing when there is no fire. And you need to have a cascade, so you do not want the emergency vent to open when a truck is discharging or charging. That's why you need to consider also the blowdown, isn't it, Anja?
Yeah, exactly. Every manufacturer will give you a detailed information about the accumulation. That means how much percentage does the valve need to be fully open. But of course, it needs also a certain blowdown, as Mark said, when it's reseating. Those who are working with real safety valves at higher pressures will be familiar with that. And the same is for weight-loaded, low-pressure valves. So always be sure that you have a certain gap between the opening points of your valves in case you have several installed on a tank. To give you a tool at the hand to do a sizing and selection, we can just shortly show you our sizing and selection tool on the next slide. It's called KISS, so it's KITO Sizing and Selection, and it's free, available on our website. No login, no registration necessary. You see here the address, and you can choose your language you are most familiar with, and it's offering as well the calculation in accordance to several international standards. So even if you're not planning to use a device from us, the calculation for in and out breathing can be useful for you, which we will see on the next slide. So you can choose which standard you want to use. So there are several ISO 28300 or API 2000 in other editions, and you can enter your tank data here, like height, diameter, where it is installed in the world, pump rates, and automatically you will get the results. In this case, we also choose emergency venting, and you see on the top line the results are shown. You can choose emergency vent in this case, enter the tank design pressure, then it selects you automatically the set pressure and the size. If you want, you can add a tech number and export a PDF file for your own documentation. Nothing is stored on the website, so just feel free to have a look at that, and it's quite useful for doing a first calculation. So we are nearly at the end, just giving an outview what else can be an application. Mark, here we have a combination of another arrestor on top of the tank.
Yes, you see it's like an angled detonation arrestor. It's quite easy. You can remove the cap and do easy maintenance. And it's connected to, let's say, an incinerator and for distance. So to prevent any explosion and the flame coming from the incinerator, you have the detonation arrestor. So, but you have also a pressure vacuum valve in the middle, and this is protecting the tank during normal in and out breathing. You see the flame arrestor element on the top of it. And for the fire case, you have an emergency vent as well.
Yeah, that was our short introduction in our field of explosion protection and the world of breather valves, which we like quite a lot, Mark. Huh?
Yes, Anja.
Thank you, Anja. Thank you, Mark. I'm sure a lot to learn in less than last 30, 40 minutes. And thank you for your speed and interaction with the audience. So we still have last 11 minutes to go. And if the audience has any questions, they can put it here in the chat function or the question and answers, and we would love to have some of them. I would also like to invite Bart on the screen, so we can have nice question and answer interactions. So in the meantime, I have put down some questions for me when I was listening to all of you. And then, as we know, some of our audience are coming from the Netherlands, and as far as we know, the flame arrestor element is not required in Netherlands for breather valves. Is that correct?
Yes, that is correct, because the flame arrestor elements are required in Germany by law. So when the ISO has been written, valve manufacturer specialists have come together, but not all of the consensus was reached. So what is obligatory in Germany is not necessarily accepted in this code. And the Netherlands has a specific law, and that was what Bart pointed out. The concern of freezing, which is indeed a major point, for instance, in the Netherlands. We do not see that in Belgium, but what we see also is that some of our customers in Belgium either decide to follow the German practice or also the Dutch practice with the concerns of icing.
Right.
Yeah, that's what we see a lot also. And of course, you can always have the option if it's for the, so on the breathing out, I see that as a different thing because there I do see that you run a much higher risk. On the breathing in, it is indeed questionable what you have to do. And if you should install it, then I think it would be a smart idea. For example, you could also, for example, install heat tracing. Then you can, of course, still have it and prevent the freezing over of the whole thing is also an option. So yeah, indeed.
Thank you. There's a question from the audience on the chat. What are the requirements for insulating and heating detonation arresters? For example, vapors of the product which may solidify during freezing weather.
Yeah, it's possible to do electrical heat tracing. It must be sure that this material is also ARTIX approved. There are several manufacturers, and of course the heating jacket is tailor-made for the shape of the specific detonation arrestor. So it can be delivered together with the arrestor, and yeah, as said, it must be ARTIX approved and suitable for the conditions.
Because Anja, in that case, I also know that the way that such a thing works is also that it actually, if there would be a flame front, it is actually, when it goes through, it's a block of steel. So you have some heat that you lose. That's what also partially quenches the flame, I would say. So meaning you would need to heat up that whole thing as well. So that's quite a big heat input that you will need probably, right?
Yeah, normally these electrical tracings are for frost protection, to avoid freezing.
Yeah.
And then we talk about temperatures which are not that high because you cannot go. The heating medium is not allowed to be hotter than plus 25 Kelvin or Celsius than the maximum allowable operation pressure temperature.
Yeah,
so
okay.
means if it's approved for 60 degrees, it must not be hotter than 85 degrees, as example.
Yeah, okay.
Yeah. So it's mainly used for keeping a quite lower temperature or avoid freezing.
All right, thank you. There is another question. What is the problem with a reduced size flame arrestor in a line?
What is the problem?
With a reduced size flame arrestor in a line.
When we imagine the explosion process in the line and the diameter is getting smaller, the energy is the same. So there is more energy on less surface. And we can imagine that that brings, more pressure to the same system. So as Mark said, this is not for what an arrestor is tested. So it is really important to follow these guidelines.
Yeah, it's critical because we see that question, at least I get that question a lot. Why not make it one size smaller? Because it's cheaper. Yeah, well, that would be the wrong way to save cash. Let's say it like that. Yeah.
Thank you. So there is a continuation of question for heating. Will heating affect the functioning of the detonation arrestor?
As said before, if the heating suits to the arrestor, it is not.
All right, thank you. So I have another question. Is maintenance important? And if yes, what needs to be checked?
Maintenance is important. We need to divide between flame arresters and breather valves, of course. Let's stick here to flame arresters. We recommend maintenance at least once a year. And what do we have to do? We have to check the flame arrestor element. You can dismantle it and you can check, is it maybe just polluted? Then it can be cleaned by pressurized air or a solvent. Important is that it is completely dry before reinstalling. Otherwise you have droplets, which may create pressure drop. But if you see any color, blue color, which will show you that the flame arrestor had stopped an explosion, then it has to be exchanged. Although a flame arrestor which is approved had been tested 5 up to 10 times with the same element to get the approval. But nevertheless, if you see, or if you know, I see the other question here, is a flame arrestor still usable after ignition? If it had seen an explosion, the flame arrestor element needs to be exchanged for safety reasons.
Okay, thank you for taking the answer. I think Mark and Bart also has some inputs for this.
Yeah, if you can put a temperature probe at the site where the flame comes, you can detect it, so you know at least when a flame arrived.
Yeah, well, if you are quick enough, because if it's a very fast flash, then you don't always need to see that, I think, but it will help for sure. One of the other points that I would like to note on, for example, cleaning, is that we have seen clients a lot that treat, off gases from, let's say, heavier products, heavier oil products from a ship, but they can have preloads, for example, of crude oil or stuff like that. But a big ship also needs to be less than 4% O2. So that means they will put their own exhaust gases into the tank, which is not exactly very clean. What you will see is that you get quite some stuff in there, which is rust, soot, and stuff like that, and it starts to clog. And that's a problem. And then what I've seen in the past is that clients then take this whole thing out, use a high pressure jet to clean it off, and then think that they have cleaned it. Well, that's also a risk, right? I would like to talk about that slightly as well, because that is not the way to clean it properly, as far as I know.
Thank you.
And that's also a critical point. Yeah.
So there is same question also from the same attendee. Can a flame arrestor to be useful for ethylene oxide?
Very good question. There's knowledge. Ethylene oxide is a very specific product because it tends to decompose, and it is excluded from the standard approvals of the ISO standard. So if you need a flame arrestor for ethylene oxide, you need a special approval for that product.
All right, thank you. So we still have 1 minute, but from the last webinar, we understand from some of the audience that please extend the question and answer session because we learn a lot. So if somebody cannot stay until after 4:30, they can leave, and we can share this recording later. Let me take some more questions. What is considered a safe distance from the flame arrester's pressure wave? For example, if a flame arrestor is installed in a zone where people could pass.
Naja, then he probably thinks about an end-of-line arrestor, because in-line arrestors, then the pressure wave.
It's just like the piping, yeah? So it will just be fine. But if it is an end of line, I think that is perhaps what is meant. So if it is in line, then it is not a real problem because it's just like the piping. So it has to be safe as long as it's truly an explosion-proof piping class, which is also critical. And if it would be...
Yeah, please continue. No, sorry.
No, but I think my first idea would be that if it is at the line end, then it needs to be placed at a point where you can't pass.
Exactly.
Wouldn't
Needs
be
to
a
go
good
to
idea.
safe location. And in some German technical rules, for example, we have the rule when you have underground tanks that end-of-line devices need to be at least 4 meters above ground. And normally there's no one to pass by.
Yeah.
Thank you.
I
I have a question. You know, PD, Pressure Equipment Directive, is this also applicable for flame arresters?
Who wants to answer?
Is it so difficult?
It could be. It could be if the operating pressure is above 0.5 bar. Usually, most flame arresters are in atmospheric conditions, so that it is not needed. Of course, we need ATEX approvals, which is something different. Both have the CE label, but the PED comes into figure if, for instance, you have a blower at 2 bar and you want to protect it with a flame arrestor.
And depending on the category in which this is classified, because the ATEX guideline says if a protective measure, which is a flame arrestor, is only classified into category 1 as per PED, PED does not need to be considered extra. So it depends a bit on the size as well. For bigger sizes, it might be necessary, whereas for a smaller size, it's still category 1. So it's a bit case-by-case decision. And can also be for vacuum valves, which are on a tank at higher pressure. So there are applications for PED.
Yeah.
Thank you. Maybe I'll take one last question, and then I have last question after that is what is that we haven't considered in this webinar? We haven't talked about it in this webinar towards the end. But the question that I noted down is, are there any restrictions in regard to the oxygen concentration in the vapor air mixture?
Yeah, that is a good question, Amal. Yes, indeed, because most of the applications, you have an ignition in normal conditions where you have air, and air has 20% oxygen. That's where the flame arrestors are tested, approved. But if you have an application where you have a higher oxygen content, for instance, due to chemical reaction or some blower that is pumping oxygen, it will become very dangerous because oxygen will accelerate. So you need to have a specific approval for the case.
Yeah.
All right. Thank you.
I think that also is the other way around. I mean, we very often see clients that have, for example, off-gas treatment on tanks that are under blanketing. And then they say, well, there is no O2 in my off-gas, so I don't need one. And if you look at the norms, de facto, they may be right, because it states what is the zoning inside of your off-gas line. And you could state, well, then it is at highest zone 2 or whatever, or it might even be not zoned. But we often see clients that still do it because of the fact that blanketing valves can fail, and you don't know that always, and then you can still have O2 in your piping. Therefore, they want to be on the shore side and ensure. So there, it is not a bad idea to add this more protection. But so it is really case by whatever you do, we need to check at what is actually happening and what makes sense and what is the actual risk. So yeah.
All right, thank you. I don't see any more questions from the audience, but for sure, if they have questions, they can reach out to hello@bmprocess.nl or connect you guys on LinkedIn and just explore more. But before we leave, I have one question.
If there's any more questions, then feel free to ask them via mail or whatnot, and we will get back to all of your questions. I can promise that we will. So we will take care of that.
Yes. So before we leave, I have one question to three of you. What is that we haven't considered in this webinar and that you would like to really, really highlight to your audience?
What we haven't?
Yes. Maybe your experience from one of the plants, good or bad, or
It could be as well interesting to talk about how to deal with mixtures of flammable products. How can you solve that? When a temperature sensor could be of interest.
Stable, unstable detonation, the difference.
Yeah. Some more applications. So.
Okay. So maybe in the future, and they can also go back to your website and look at the applications, and maybe in one of the webinar focusing on specific applications as well, if there is a need from the audience. You, Mark, and Bart, anything that you'd like to share, your experience or important information?
It's indeed the question that I want to know two things. What we very often see, because we hardly ever treat a pure off-gas. It's always a mixture that you can't really fixate, can't really predict. It can be all over the place. So how to handle that? That is indeed a good question that I can talk about, but we can do that afterwards. For the rest, I want to say that the tool that we were just shown, I think that is an absolutely super cool tool to use to choose and to have a first idea that really works extremely well. So yeah, very, very helpful.
Thank you. Mark, do you want to add something, or we can just conclude quickly?
I very much like the coyote in Bart's presentation. This was my favorite in my childhood. So.
All right.
He's still cool.
Right. So in the weekend, we can watch some of the series about it. All right, Anya, Mark, thank you for being guest at BM Process Management webinar. Thank you for sharing your expertise and knowledge. I'm sure, as usual, audience learn a lot through our webinars. There will be a few more coming in throughout the years. Please stay tuned. Bart, thank you for answering some of the questions and also explaining with some real examples in the beginning. And the audience, thank you very much. I saw some messages, so please stay in touch. As we mentioned, easiest way to reach on the email or LinkedIn, and we ensure that next time if there is safety-related questions, we have right partners, and also we are happy to support you whatever we could. With this, I would like to conclude, and our live webinar will also be available online on YouTube in the coming days. So thank you very much, and I wish you a wonderful rest of the day. Thank you.
Yeah, thanks a lot.
Thank you.
Thank you.